Okay, so you can look at a star cluster and see it's blue or it's red or whatnot. And on that basis, make an estimate of what you think the mass of the turnoff point is. You examine it, you look at this, and you can tell by looking at its Hertzsprung-Russell diagram, HR diagram, you can actually tell how old the cluster is. Now remember how this is done. You measure the brightness on the telescope, and then you solve the equation of the brightness. You know that that varies as the absolute luminosity divided by 4 pi d squared, where d is the distance. And you will find the distance of the star. And so astronomers learn how to use spectroscopic parallax, this is called, even though it's not a parallax at all. It is using the spectra, and this enables them to estimate the distance to the stars. All right. All right, so the formation of these stars is before the star forms. It is generally in a molecular cloud. These are around the galaxy, and they are the birthplaces of stars. They're very cold, they're very dense. Okay, the molecular clouds are extremely cold. You know, I can never remember which button to push. All right, and these cold clouds can fragment as they shrink a little bit, and the cores can become more compact and become the fragments to make new stars. Now, the first issue is that something has to happen. The star will not form unless there's something around there. If you've got a cloud and if you push on it, it may collapse a little bit. As you push a little more, it might collapse further. Eventually, it will get hot and radiate. It'll be a protostar. The star that continues collapsing until it reaches this very high temperature, 10 million degrees. And then it gets to the proton-proton chain, finally reacts of the star. If it gets to that temperature, it's hot enough to overcome the barrier to prevent it from forming. Okay, now this is a star. Here is the Orion Nebula and Betelgeuse around it. These are actually infrared pictures taken of these clouds of Orion. These are regions where stars are forming now. It's right in the middle of formation. Another is this picture of this beautiful pillars of creation in here. This is a very famous picture. This is where stars are born. That is a blue star that's heating up the clouds. It's burning off a lot of the covering material in there. Let's see now. I think I can make this thing play a little bit. Okay, so we're zooming in on a part of the cloud. The part of the cloud is going to be around here, say, and this is a knob that, or over here, this is a little knob that is a whole solar system. It is not the big cloud, it's a tiny little knob on that cloud is our solar system. It's a little hard to believe it, but this is a molecular cloud in the formation of stars. The stars are just little knots in the middle of this huge cloud that's all being eaten away by a giant star nearby. But in the middle of this are hundreds of stars being born. You might form one star every million years, very slowly. But this is how the process works. It's pretty amazing to realize what the hell is going on. Okay. A lot of times you have this beautiful cloud gets burned away and it leaves only the blue stars behind it. So this is, we estimated last time that this thing is probably 50 million years old. And 50 million years ago, it probably looked like this. And then all the gas got burned off from it and left this behind. It's pretty amazing. 50 million years is nothing. You know, that's no time at all. Okay, so the stars go through these manipulations. They're dense. They rotate a little bit. There's a cloud here. And the cloud shrinks due to its own self-gravity. It shrinks and shrinks and shrinks. And remember, the star has all this angular momentum because it was rotating a little bit. The star has to get rid of that spinning nature of the star right away. One way it uses to get rid of this excess spin is to throw jets out from the north and south pole. And that is something that can carry away some of the angular momentum that it has. This is interesting. The angular momentum is a conserved quantity because as your star shrinks, it's like an ice skater. She's spinning too fast. She pulls her arms in. She's spinning real fast. So what does she do to not spin faster? She drags her heel. It won't spin so fast. All right. Now, stars can't drag their heels, but they can do something like shoot this angular momentum out. Okay. Protostar rotates faster. The material falls in, and you might form planets out here. Maybe you will. All right. So eventually, it will come down. You'll come down to a disk spinning fast, a star spinning fast. Everything's spinning a little too fast to condense down to a core that will burn helium or burn hydrogen. It's all spinning fast and getting rid of it. And these jets are thrown out when that happens. And sometimes, here's a picture of one. A disk is in here, is absorbing. The disk is that. There really is material right in there. And here is a jet it's sending out, just like there. That's a star forming, known as a protostar. It's forming right now. Okay, here's another system. There's a star there. It's blown out material here and here, just like this. It blew them out because it was born with too much angular momentum. So it's spinning out some of it. Okay, the star heats up. It radiates a huge amount of thermal energy. And the star is kind of a little messy situation. It's not in equilibrium the way we talked about before. The star has a tremendous amount of agitation in it. Energy is transported to the surface by convection. It boils a lot. And it's getting rid of the angular momentum. And all this process, all this heating is going to stop when the star eventually reaches the burning temperature of hydrogen of 10 million degrees. But until it gets there, the star is a little bit chaotic. All right, so what's happening is here's the main sequence. And let's make a star right here. You start off with a star that was formed out of a gas cloud. The cloud is out here, temperature less than 3,000. It's probably a temperature more like 300 or 30 degrees, very, very cold. The material collapses, and the protostar, so-called protostar, collapses and shrinks. All the while, it's heating up, heating up, heating up. Now remember that luminosity is plotted here. It's heating up, it's becoming, it's getting over to the main sequence. It's heating, and then eventually it starts shrinking, and it's now the star is huge, and it has to convert some of its gravitational energy into thermal energy. It heats up. There it has all these different stages, and it goes through these manipulations. None of these stages are really important. It goes through these different stages that are known. But the star is basically settling down. And it takes a while to do it. If you're a big star, you're going to go and settle down here, and that happens very quickly. It'll settle down in 5 million years. If you're a light star, you'll struggle and settle down over here, and that might take 50 million years. So the time scale for settling on the main sequence depends on the mass of the star. The mass of the star governs everything. All right, so the star has a way of going from a gas cloud to a position on the main sequence. All right, so the arrival on the main sequence, here are some trajectories of arrivals. A star that's 15 solar masses doesn't take very long at all. It just zoop. It finds itself on the main sequence in no time at all. Just zips along. Here a star at less than the sun, maybe it won't take 60,000 years. It takes 150 million years to get there. Very slow and sluggish. It finally climbs onto the main sequence. Now, these calculations are something, they're not something you should remember. You should just understand that a star, when it's burning hydrogen, is on the main sequence. Before it burns hydrogen, it's not in equilibrium. It is adjusting itself, settling down, and in the process, it's somewhere on here, but it's moving this way. It's moving to the main sequence. Once it burns all the fuel of the helium, once the hydrogen all converts to helium, it's going to leave the main sequence, and the sun will go up here and dance around a little bit. The 15 solar mass star will go off. But it go off in the same trajectory in which it came on. It'll go off. So these stages are what is happening while the star is moving and burning. Okay, so the mass of the star determines everything. How long it takes, where it's going to land, what the spectral type it has once it's there. So, we talk about a population of stars. In any distribution, there is a population of stars that are heavier, that are lighter. It's like the population of wealth in this country. If you're lucky enough to be born into a lot of wealth, you have that wealth with you, and generally you don't lose it, and you've got it. If you're born with very little wealth, it's not that easy to change to a situation where you suddenly have a lot of wealth. You can do it, but generally you don't. The mass of the star is something it's born with, and generally we'll talk about how it loses mass, but generally the star does not gain mass at all. Okay. All right. Now, if the star is less than 8/10 solar mass, it'll never burn. The star is stillborn at that time, and it becomes something. It's not a main sequence star. Instead, we call them less than 8/10 solar mass. They are called a brown dwarf because they're brown. They never really burn hydrogen at all, and so it's a brown dwarf. We've actually seen a few brown dwarfs in the sky. It's difficult to do that, but it has been done. Okay, they're very faint. They emit infrared, and they are made of hydrogen. We say their core is degenerate. Who remembers what degenerate means? Anybody? I told you about degeneracy pressure last time. Anybody want to tell me what is it to be degenerate? Come on, somebody must remember what I said. What is the degenerate star? Anybody? Huh? What is degenerate? You guys, don't be too shy. You know what degeneracy is. It's what? What about Heisenberg uncertainty principle or the Pauli exclusion principle? Does that have anything to do with this? The degeneracy pressure. Remember, the degeneracy pressure is what happens when you're trying to sit in the seats here, and we go one night and clean all the seats out except for 10 or 20 seats. And then you come into the room the next morning and you bounce off the walls trying to find a seat. Remember that picture? Bouncing off the walls. You bounce off the walls and hit the walls and push them out. You are exerting a pressure on the room by just being there, and you are degenerate, meaning you can't find a position for you to sit in. Degeneracies like atoms are degenerate when they don't have quantum states they can reside in. So a degenerate star is a star that is held up by quantum mechanics, degeneracy pressure. The star is massive, and it's not necessarily burning. It effectively is like zero temperature, and it has pressure on the walls that it's sitting in. So that is degeneracy. We'll see. We'll use it more in the course as we go on. Now, from the ground, from Palomar Observatory, people have actually seen, here is a brown dwarf. Not that you can tell anything. From the Hubble Space Telescope at about the same time, 1995, they have better optics, and they saw the same star, same brown dwarf. It doesn't look like anything there, but this star weighed less than the magical number of 0.08 solar masses. So that's a brown dwarf for what it's worth. Okay, and we also talked about the craziness of stars. Did I talk about all this last week? Did I talk about this? No? Okay. Wow. All right. So we spoke last time about the evolution of the sun. The evolution of the sun was a typical main sequence star. The sun had a core, and it has a envelope that carries the radiation from the core by radiation transport. And then it comes to the outer portion of the star where the material boils, just like we saw in the solar granules. And the sun is boiling out there, and it's called convective. Just like the Earth is boiling. The Earth is boiling. These convective cycles makes the Earth turn over. It's what powers the circulation of the Earth. It's boiling of the Earth underneath. Okay, so that's what makes the sunspots. And sunspots are seen to, the area that's boiling is a certain radius region. On a very light star, low mass star, it turns out that nearly the whole star is outside the core. Nearly the whole star is boiling, convecting. And this will give rise to flashes of very exotic types of behavior. But that is known. Bright stars, on the other hand, don't boil at all on the outside. They boil on the inside. This core is right there, and they're boiling a little bit, and then it swings over to a region that is not boiling. These are all details that have been worked out, and they're all known. This was mathematics, has all been solved, and they know how long these stars live, how long they'll be on the main sequence. Okay, so everybody stays on this main sequence until they burn up their fuel, and their fuel is hydrogen. Once they burn up the fuel, it has to move, it has to do something else. What does it do? Okay, so the massive star is burning up faster, and then they're stuck. You've got a massive star that's burned up all this fuel. What is it going to do next? Now, it can't sit there. Remember that if it just sat there and didn't do anything, you say, well, just so what? It won't burn in fuel anymore. Well, then what's going to happen? You've got a huge mass pushing in on the outside, and the inside has no burning is generating in the inside. It's not generating any pressure to push out. So it's got a strong push in and a very weak push out. So that means the push in is going to win. It's going to push harder. And that means the central temperature isn't going to sit at whatever it sits at. It's going to be pushed harder. That means the central temperature will do what? Will it go up or go down when you push on it? Up. And that, of course, is the crazy thermalness of stars. As you push on them, they don't get cold. The central region gets hotter. It gets hotter. As the star gets squeezed, you may be in a lower energy state, but it still is a hotter state. As a star is up here and goes down there, it may lose energy but become hotter. The hotter star finally gets hot enough to burn the helium. Finally gets hot enough to burn it. So let's look at this again. Okay. All right, low mass stars have convective outer layers. And this means, what does it mean? Take out your cards. Does it mean they're like the sun? They can have star spots. They can have flares, emit X-rays, all of the above, or A and B. Which do you think it'll be? So, okay, who's got your cards ready? I only see a few. Talk to your neighbor. If you haven't got a card out, you have to talk to your neighbor to figure out why. Talk, talk, talk. Yeah, that's right. All cards. Right. Okay, let's go on now. Who says it's red? You've got a bunch of you. Yes, they're like the sun. They're convective outer layers. That's like the sun. Okay, so red is possible, but they can have star spots too. They have star spots the same way the sun can have sunspots, where a magnetic field leaks through the sun and produces a sunspot. So B this is also true. Emit X-rays, well, no. They're not hot enough to do that. So that isn't really true. See, the green is not true. All of them aren't true. White is the answer. A and B are what the star can do. So these stars, and most of you had white, so that's good. All right, these faint stars can mimic the sun's activity, but that's about it. Okay, now, all right. Okay, so this I think we saw the other day. Suppose the star, we're dealing with a star that weighs just about that of the sun. The mass of the star is dialed in here. I dialed it to about the mass of the sun. Elapsed time is 0, and we'll begin this evolution. And over time, the composition grows and grows and grows until it's 100% helium. All this region has become helium, and that took 10 billion years to happen. All right, the luminosity is just less than that of the sun. Okay, so let's turn this up. Let's turn it way up. Why not? 100 solar masses. And it goes out of fuel. But the whole thing burned through all of its fuel in just until 1 million years. That's pretty short. So that star isn't going to be around for long. Or we can take a star at the other extreme. Say, let's try, well, 40% that of the sun. And this one burns. And this is 10 to the 11th solar masses. Now that's so long, that's longer than the age of our universe, which is, well, no, it's just longer than the age of our universe. So, okay, we don't worry about those, but those stars more or less are, once they're lit, they're burning, and they never burn out for all effective purposes. So 4/10 is the mass of the sun, and that one lasts forever. And this is just an example to show that if the mass gets high, they don't last very long at all. Okay. Okay, so the first point, we've talked about the burning of the hydrogen core, and now we're going to burn, the hydrogen core is after a while completely depleted. And now we have to say, what happens next? So the star, like the sun, is sitting here on the main sequence, and then it's going to climb up here, going through several phases. The first phase is called subgiant, and then it goes to something called red giant. And this red giant because the stars get redder, giant because their luminosity goes up. So how does that happen? After the star has, it has burned up all its helium. So the core is going to collapse because the pressure of the stuff pushing it is just huge. Pushes it, begins to collapse. Okay, now as it collapses, the hydrogen shell gets hotter, the material in the core was all depleted. Material in here is all helium, it's all shrunk, but the outside of it is hydrogen shell. It's hydrogen everywhere, and this shell is hot enough to burn hydrogen. It burns hydrogen in spite. See, now we're not burning it in the core, we're burning it in a shell, this little red spot. And the core is inert. Nothing's happening to the core. It's inert for a bit. And there's less gravity to hold it from above about this point. That means it's going to expand. The star is going to expand a lot, and that pushes it out. Okay, now this phase is called the subgiant phase. It's doing that. And finally, it's going to get to the stage of producing 3 heliums are going to collide and produce a carbon atom. How does it do that? The helium collapses until it reaches an incredible temperature of 10 to the 8th degrees. Remember what I said before about the barriers to prevent Okay, a proton comes in, or in this case, helium comes in, and it tries to hit another helium atom, but it has to overcome a hill. It has to climb up over a hill, and then it can leak down into close proximity. This is radius plotted this way. So think of the proton coming along, hitting a hill, bouncing off, and bouncing back. If you're on a bicycle or a wagon and you run to a hill, you never tunnel through it. You'll go up a certain point on the hill and then you turn around. That hill is produced by the electromagnetic repulsion. The protons in the helium all have positive charge and they repel each other. They don't want to get together. So it comes in. Now we know last time we said if you come in at a high level, then you have a higher chance of getting through. Higher and higher chance. Now this might be the barrier that you could draw for hydrogen and a hydrogen. But if you're talking about a barrier for helium, then the barrier is very much bigger. And you have to, at a low energy, the star is never going to penetrate this barrier. At a high energy, it penetrates still very poorly, but after you get up here, the energy is high enough, you can occasionally get through there. And that corresponds to a higher and higher temperature. You have to heat the central region not from 10 million degrees, but you have to get up to 100 million degrees. Finally, the energy is high enough that you can barrier penetrate occasionally, and you can actually burn helium together will make carbon. Now, 100 million degrees is ridiculous for anybody to imagine building. We can't reproduce this. This is something the sun is not hot enough to do. It's not enough pressure to do it. You only do this in the center of a star that has burned through all of its helium and burned through all its hydrogen, leaving only helium. So it's very, very exotic. This is not something that happens every place. This is an exotic phenomenon that happens only in the centers of very massive stars. So it was quite astounding to realize this. All right, so Now, there are lots of problems. The first problem, I think I mentioned this, is that it is very, very unlikely that you're going to get 3 atoms together to form a carbon, to form something like this. It takes 3 of these things to all merge together, and they make a carbon nucleus. That is very unlikely, because you never get 3 of anything to hit at the same time. You know, think of billiards. If you're striking a billiard ball, the billiard ball strikes one and then hits another, hits another, hits another. Well, that's fine, except they are not hitting at the same time. That billiard ball never hits two other balls at exactly the same time. Does anybody think that it does when they play billiards? How many did you think you hit at once? Well, you're hitting one against another. But you think you can hit it, that means you got to have perfectly aligning them, going right between them. That's probably unlikely. You know, they're probably differing by a nanosecond or something that you can't see, right? Yeah. Okay, you're trying to split them, but usually it's very hard. And here it's very hard to have this collision be exactly right. This is not something that happens. It's very improbable. Okay, but we'll talk about that a little bit later. All right, so what happens is the star it has become a red giant. The star is doing this in the center. The helium, which had been sitting there, it couldn't cook because the temperature was too low. Eventually, the temperature gets hot enough to let it cook. It cooks and cooks and cooks and forms the carbon in the center. So you have carbon cooking away in the center of the star. Okay, so now we have a reproduction of what we had before. The pressure from the outside is pushing in, and the heat from this reaction is pushing out. All right, so this is life. This is an incredibly important reaction. Of course, we all need carbon to live. And believe it or not, this is where all the carbon is made. In this hellhole. You have to be in a spot of the universe that is up to 100 million degrees for some time, a brief time. But it has to do that. It is not, you don't cook it at a low temperature, 100 million degrees. And that's one stage. All right, so what's going to happen now? At the center of the star, you've got this fusion going on. What will we see? All right, you've got the core in the center has helium here that burns the carbon. It has outside shell around it that is burning hydrogen because it's easy to do that. Hydrogen has a very weak barrier. Remember, you only needed 10 million degrees or so, and you cross the barrier. The hydrogen burns and the helium burns. And all that's inside the star. Meanwhile, the star has gone up the subgiant branch, and then it goes up the giant branch once it starts burning the helium. Stars that ascend the giant branch for the first time, all right? And eventually, the star blows up. The star here expels all the material on the outside. And what happens is the star, hang on. All right, the red giant exhausts the helium fuel. What's left over, this carbon core, it collapses a little further. Low and intermediate stars are not heavy enough to do this. They cannot do that, so it just sits there. These shells of helium and hydrogen burning. They overcome gravity and propel the outer stuff away. And this is a fairly gentle wind. It's not blowing too hard, but it is expelling all the material. Wait, there's another picture here. I thought I had another one. No. Okay, sorry. This is a planetary nebula. You could see Adam or Isaac. Are there any planetary nebula for viewing now? There must be some. Probably too hard to see it. Yeah. This is not something you can see in a bright spot like Berkeley, but these are pretty objects. And this star has blown up all the carbon it formed. So what's it going to do then? The star is going through this crazy manipulation. First it goes here and goes up there, this red giant phase. Then it goes down and goes up. This is this star goes from helium burning to hydrogen burning, helium burning somewhere. You get inert cores of craziness going on. And it gets more and more complicated as the star is just trying to burn its fuel. And what it does then is eventually it turns itself into a planetary nebula where it just blows off the outer stuff. Just blows it apart. That means everything outside the core is blown off the star. And a lot of material gets ejected from the star in those cases. The star blows itself up, and the only thing left is the core. It's probably a core of pure carbon. The carbon core, then eventually it wanders over to this region and wanders into this point right here, and they're called white dwarfs. That is, a white dwarf is a degenerate dwarf that has blown off all of the outer envelope of it, and this is where it sits. The core you can't get rid of that core. It's tightly packed, and this is the material that is left when the rest of the star is gone. And this is something we can see. We see these cores as companions to other stars, or we see them in other ways. But these are, first of all, incredibly exotic. These have about the size of the Earth, the mass of the sun, but the size of the Earth. White dwarf. They're white because they're so hot, typically 20,000, 40,000 degrees. And they settle down somewhere on here. As they cool down, they'll move this way. But it takes a very long time for them to cool. So this is a crazy behavior of some of these stars. They burn through that mass and eject all the outer shells. They eject the carbon shell, which later planets will form and pull in some of that carbon. And that carbon is, of course, necessary for life. But there's all these complications. We're not going to study all the complications of the stars. It's really not important for you. But just note that stars do all sorts of crazy stuff. And they're trying to get rid of some of this material. All right, now let's ask again. Once it becomes a red giant, makes carbon in its core, why doesn't it make heavier elements? So think about your answers. It's near the end of its life, doesn't have time, not massive enough to make hotter. Heavy elements all go into planetary nebula. What do you think the answer is? All right, so talk to your neighbor about this. Come on, you guys. I know you've got to talk to your neighbor, otherwise you can't figure it out. Ah. You have an answer? Get out your card. You got to have a card. Where's your card? Here. For those of you who forgot your cards, I still have some. Not many. But I have some. Oh, you've got some. Ah, I see. All right. Well, take it. All right. Anybody need cards because you're not showing them? Here. Come and take some. Anybody need cards? You come and get them if you're not showing it. Okay. Why don't make these? Why doesn't it make? Why does the star not make heavier elements? Runs out of fuel? No. But it's not massive enough. That's what the answer most of you have. It is simply not massive enough to light the furnace hot enough to finally cook the heavier elements. If you're going to, you've got to get the temperature, believe it or not. This temperature to make the triple alpha product, to make carbon in the center of a star, was a miserable only 100 million degrees. And if you're going to cook heavy elements, you've got to get the temperature up to 1 billion degrees. That is so ridiculous. You can't, it's impossible. We're having an incredible time getting the temperatures in a furnace over 10,000 degrees. Here we're talking about 1 billion degrees. But that is necessary if you're going to make heavy elements. You're going to make iron, gold, anything. Anything beyond carbon, you've got to really get hot. So where is that going to happen? These red giant stars you thought were massive, but they don't seem to be able to make heavy elements. Why? Where, therefore, we're going to get everything else? Sorry? I'm sorry, just anybody? What's going to explode? The star will explode, but what kind of star? See, the thing is, we've now talked about typical stars, and they don't get hot enough to cook anything past iron, sometimes oxygen, and they don't make it. So in that case, how do you get iron? How do you get the iron or gold that we find on the Earth? Where did it all come from? Sorry? I'm sorry. Blue stars? Well, many times they can't do it. But okay, we'll talk about that. Yeah. Yes. And so we'll get there. Next lecture, we'll see how to make super heavy stuff. Yeah, you're right. Our star simply doesn't get hot enough to ever go beyond the white dwarf stage. And so you need a heavier star to do that. A real heavy star. Oh well, I think I'll. Okay, how can I get rid of this stupid thing? This is interesting. Wait a minute. Whoa. All right, well. All right, well here's pretty, these are nebula. This is what our sun could do after it burns out. Isn't that pretty? Twin jet nebula. This one was pretty, I'm sorry we can't see it. Oh, damn it. Come on. There's got to be a way. Here, let's see. Okay. All right. So these stars, like the sun, just run out of fuel, and at that point, they call it a day, and they make the Ring Nebula, for example. This is visible from Berkeley. It doesn't look so pretty. That's the star. That's the core of the star. This is all the junk it threw off. How's that one? Hourglass Nebula. Isn't that beautiful? Now, this is seeing it has lots of material that were pushed out as rings. This ring, 1, 2, 3, 4 rings, I guess, are pushed out. It's not really spherically symmetric, but it pushes them out. And this one has an eye looking at you. Okay, so this collapsing core will become a white dwarf. And then let's talk about here. Here's the history of the Earth. Now we're plotting billions of years. We go 0 to 10 billion years is the contraction of the protostar. First of all, contraction of the protostar, then the main sequence burning time, and this is where we are. Note that the main all this time, the Earth is getting warmer and warmer and warmer. But then when we get to, I should say the sun is warmer and warmer and warmer. After you go into the main you pass the main sequence, the star will go through manipulations, and it will have a helium flash, and then helium core burning, and that only lasts 100 million degrees. This is billions of years. 100 million degrees is here. This thing lasted 10 billion years. And then it goes into another ejection. It wanders all over the place and throws off this gas, and this is, it doesn't really know what to do. It pulses the material and eventually blows off the outer envelope, and what's left goes to a white dwarf. You see how quickly that occurs. 13.365. This is really computer models that told them how to do that. Now, one question with this thing is, I guess I didn't have a question. One question we asked, we've answered it once already, is if the sun has been increasing slowly, why didn't the Earth freeze in early history? Why was the Earth unfrozen? When the sun was just formed, it was about 70% of its luminosity. And today, if the sun became 70% of its luminosity today, the Earth would freeze instantly. But 5 billion years ago, the Earth didn't freeze. The Earth, it had a lot of carbon dioxide at that time. The Earth was born with a ton of carbon dioxide in the atmosphere, and it took a long time for it to dissolve in the oceans, making all the limestone and dolomite that we see. A huge amount of carbon dioxide. All right, let me show one more thing here. Okay, so let's play. We're going to play now the evolution of the core of the star. Here's a star right here. It's a G2 star like the Earth. And I'm going to turn it on. So let's zoom in first of all. It's slowly cooking, 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 cooking. All right. Yeah, what's happening? Running. Okay. Okay, the core is shrinking. This inert core has shrunk all the while, and meanwhile hydrogen is burning on the outside. The star has moved off the main sequence, and the star has gotten larger and redder. So that is what is happening to the star. If we now let it go a little further, the ignition eventually, the helium burning, which was inert, is eventually going to get hot enough. Eventually, the core is going to push it, and this temperature will get hot enough. It will overcome the barrier. So now we let it go, and bang. Now, what's happened is the helium burning in the core, goes down in brightness. Hydrogen burning in the shell. Now, think about what's happening here. You've got helium burning in the core. Helium is sort of inert and not doing anything. Hydrogen burning in the shell. So you've got two places where the star is burning, in the core and out here. And there's a layer between that's not doing anything. The star, meanwhile, has shrunk a little bit. Okay. The star, here it goes back up the red giant branch. This is the second, known as the second ascent. First one ascent, then another ascent. And now the star has become very red, very big. The core is in the center. It all burned, all the helium is burned to the core, carbon core, hydrogen out here. You've still got two regions of burning, helium shell burning, hydrogen shell burning, and these regions between them. This is incredibly complicated. So here we're going to stop a little bit. It's going to zoom out, and bang. Suddenly the star just has had enough. It throws up a little bit and expels everything out of its star, and just can't take it, and he goes into a white dwarf old age. So all stars that are retired have gone to the old age home in the white dwarfs. All right, and that's where they rest. But that is how the star sequences everything. Now, in the course, astronomers have learned this through tremendously painful, a lot of fighting and debating and this and that and the other. This is all worked out in the 1950s and 60s. We know all this is pretty right. It meets all the observational tests that you can make up. It fits all the data. There's very little data that can't be perfectly explainable in terms of how the star evolves. So I'm telling you this story because it's new to you. It's not new to me. It's not new to colleagues who work on this material. But this is a classic piece of astrophysics. How are the heavy elements made? What happens to a sun post main sequence? So we've worked through all the details of what happens. Later we'll see what happens to the main sequence or post-main sequence of really heavy stars. So that's important because it has a tremendous amount of use. But anyhow, I think that's enough for today. I should say, I'm not going to be here on Thursday. The lecture will be given by Yok-Young. I'm going to be in Munich. She can tell you why I'm going to Munich, but it's to receive an award. You can read about the award in the web pages.